morning, dear students. In the previous class, we have seen about the basics of transistor. We said that there are two types, PNP and NPN. Happy New Year, Aish. Now from this, we said that it will be having three parts, emitter, base and collector. So emitter will emit, base will act as intermediate part, and collector is designed to collect. So we have seen that the doping of emitter must be high and collector must be moderate and base must be less. And we have seen for the reason for this. But the reason was that base it will behave like a region of huge resistance. So because the emitter, the charge carriers from the emitter must be forced to enter into the collector. They must be forced to enter into the collector. We purposefully kept the width of the base as low as possible. And coming to the sizes, okay, this is emitter is medium, collector is large, and base is small. And along with that, we have seen the circuit symbol. So for a Pnp transistor, the arrow will be pointing in. For a Npn transistor, the arrow will not be pointing in. That means it will be pointing out. In both cases, okay, that was just a logic to remember the diagram. But in reality, the thing is that the emitter-based junction, okay, the direction of arrow indicates the direction of the current in emitter-based junction. Direction of the current in emitter-based junction. Is that okay? So this is what we have discussed in the past. Now, in today's class, what we'll be doing is that we'll be trying to talk about the biasing. Okay, we'll be trying to talk about the biasing of this transistor. You see, in the past, we had only P region, N region in case of a diode. So we had only two types of bias. Okay, if we ignore the no bias condition, we had forward bias as well as reverse bias. Whereas coming to this case, we have two junctions. Clear? We have emitter based junction and we have collector based junction. Clear? So let's talk about emitter roughly. Let me write about the emitter based junction. Okay, what are the possible types of biasing? Emitter based junction, and collector based junction. So let's talk about emitter based junction and collector based junction. Emitter based, collector based. Now coming to this, we know that the possibilities are easy. Forward bias and reverse bias are the possibilities. So 2 into 2, totally there will be 4 combinations. Clear? So this is forward biased. This one is reverse. This is also forward biased. Clear? So forward bias, forward bias. This will be forward bias, and this can be reverse bias. Clear? And this can be reverse bias, and this can be forward bias, or both the junctions can be reverse bias. So our main goal is to see how is this one behaving in all these 4 cases. In all these 4 cases, in fact, this is nothing much difficult. Okay, this is nothing much difficult. So this particular condition of forward bias and forward bias, okay, is what is called saturation mode. Okay, we'll see why it is exactly called saturation mode. Now, if this is forward biased, the emitter based junction is forward biased and the collector based junction is reverse biased. This is what is called active mode. Now, the reverse bias and forward bias, the third case is exactly opposite to that of the second case, right? So this particular case is what is called as reverse active mode. Because the device will function in exactly opposite to that of the active mode. So that is what is called reverse active mode. And this reverse bias and reverse bias case, this particular case is what is called cutoff mode. Cutoff mode. In fact, you can say that the in saturation mode is nothing but on mode. This is cutoff mode. That means reverse bias, it's off, and forward bias and reverse bias, case, that the case 2 will be the actual mode in which the transistor will be functioning. To understand this functioning properly, let's consider one type of connection. Okay, let's consider one particular, let's see how we exactly forward bias and reverse bias this. Here I've biased them, right? So out of which, here itself I'm revealing the secret that we'll be using this in the active mode. Understood? We'll be using this in the active mode. Let's see how it is properly connected. So for that, particularly, we use a particular type of connection called common base. It is called as common base configuration. From the name itself, configuration means arrangement. Is that right? In fact, we use the term configuration in many places, potential energy, because by virtue of its configuration, by virtue of the arrangement of the system. So configuration means arrangement. By the term common base, common base means base is common to the other terminals. So if you choose base as common, what is left? Emitter and collector. Okay, they'll be the terminals which are left. So base must be common to both of them. So in that case, how we can draw the circuit diagram? You see, base is common to both of them. So here the diagram will look something like this. This is emitter, this is base, this is collector. For ease of understanding, let's consider PNP transistor. You see, the arrow is pointing in. So that is a PNP transistor. I've chosen a PNP transistor for the explanation purpose of explanation, but in reality, we'll be using a NPN transistor. Okay. So in this case, coming to the active mode connection, So here, look at the terminals. Let me draw a terminal from here. Okay, these are the types of connections which we can make. Okay, we are supposed to make the connection in this manner. So coming to this, we said that we have chosen base as common. You see here, base is common. The connection what I'm going to make, whatever I'm going to make, you see in this case, base is common to both of them. Understood? So preferentially, what we'll simply do, just to make sure that base is common, we'll ground the base. Okay, we have grounded the base. Now here, this is a PN transistor. So coming to the active mode, for this emitter base must be forward biased and the base collector must be reverse biased. So emitter base must be forward biased, means what we have to do, we have to connect in this manner, that this P terminal, P type must be connected to the positive terminal and N type must be connected to the negative terminal. Is it done? So is this forward biased? Is this forward biased? Yes. So now this one is forward biased. A forward biased this, and this particular voltage. Okay, this is what is called. Actually, this should have been called as emitter base voltage. Okay, voltage of emitter with respect to base. Okay, this must be called as voltage of the emitter with respect to base. And here, coming to this, if you want to reverse biasing, then what must happen? The N side must be connected to the positive terminal and P side must be connected to the negative terminal. This is positive, this is negative. So what we have done here, we have connected this in reverse bias mode. So this is forward bias, this terminal is reverse bias. So this potential difference, this is called as voltage of collector with respect to base. This is considered as voltage of the collector with respect to base. Now you might be confused. In fact, I've made a connection in active mode. Okay, I've made a connection here in active mode. That the emitter base junction is forward biased, the base collector junction is reverse biased. So you might be surprised. Then how to remember this? Okay, you might be worrying how to remember this actually. Out of the 4 cases, how to exactly remember this circuit means, look here. Where is the direction of the current? The direction of emitter current is here. So this is the direction of emitter current. Is that right? So this is the direction of the collector current. So in fact, if you can see, the direction of this external voltages applied will exactly match or tally with that of the direction of the currents in the emitter and collector. Do you agree with this? You see, this will be emitting current. Okay, the current will be flowing from positive to negative from outside. You see, positive, it went, if you can see here, it went in this manner. Then from there, it came like this. Understood? This is a proper direction. Okay, this is a proper way of connecting in active mode. Now, if you similarly try to connect, this for a NPN transistor, then how we can do that? Let me simultaneously draw for a NPN transistor. So coming to the active mode, so how do you draw NPN transistor? In a NPN transistor, the arrow will not be pointing in. So this is a NPN transistor. So there is a direction of current. Direction of current is in this manner. So the emitter current will be supporting the direction of the arrow. So this is the emitter current. So this will be the collector current. So how should you represent? You see, the current must be moving in this manner. The current must be moving in this manner. That means, you see, that is voltage across the collector with respect to base. Here VEB VCB means collector's voltage with respect to base, emitter's voltage with respect to base. That is collector base. So here this must tally with the direction. So that means, you see, it must be connected in this manner. Do you agree? You see, I'm not saying whether it is forward biased or reverse biased. I'm simply applying the voltages so as to support the direction of current for a NPN transistor. Do you agree with this? Yes. Now then, what do you have to do? Simply join the base. Simply join the base. So this is the emitter, this is collector, this is base. Now check whether this is in active mode or not. In active mode, what must happen? The emitter-based junction must be forward biased. If you can see, the P side is connected to the positive terminal, N side is connected to the negative terminal. Here, so this is forward biased. Yes, this is forward biased. Here, it was supposed to be reverse biased. Check. N side to the positive terminal and the P side to the negative terminal. So this is reverse biased. So without knowing what way I'm connecting, okay, if I make sure that my connections support the direction of current, the direction if they support the arrow, that means I've connected that in active mode. So this is the proper connection. In fact, you see, without even knowing about the transistor, its behavior, all the things itself, just we made sure that our external applied voltages are supporting the direction of the arrow in the transistor symbol. So that's the active mode. That's how that's a proper connection in which the device will function properly. So this is a NPN transistor. You see, if I want to talk about this connection, I have to say that NPN transistor in here I have connected both the voltages with respect to base, right? So NPN transistor in common base mode, common base configuration, particularly in active mode. In active mode, got the logic? In active mode, That depends on the voltages which you are applying also. So that's the reason why here I'm ignoring this point, because the in though we make a connection in this manner, by changing the magnitudes of the applied voltages also we can change the modes. So that's the reason why I'm not mentioning the active mode here, but that was supposed to be the proper connection. Now look here, actually this was supposed to be called as emitter based voltage. Voltage of the emitter with respect to base, voltage of the collector with respect to base. Here voltage of the emitter with respect to base and voltage of the collector with respect to base. But how people usually call it is, okay, they call it as base emitter voltage and collector base voltage. It's a habit of the people. Okay, instead of writing VEB, they write VBE. In both cases, they mean that's the potential difference between the emitter terminal and the base terminal. VCB means that's the potential difference between the collector terminal and base terminal. Got the point? So here I request you not to be rigid on the notation. That means VEB or VBE means the potential difference across the base emitter voltage. VCB means the potential difference across the collector and base terminals. Now here, to understand this, what we'll do is that, you see, this is a Pnp transistor, right? This is a Pnp transistor. How we have connected? We have connected it in this particular manner. So look here, if I take a Pnp transistor, if you have understood today's class, that means you have understood everything. Here, they say, right, a good beginning is half ending. It's something like that. This is base. This one over here is emitter. We are biasing it. It is important and it is easy only. It appears to be difficult, but in fact, it's not difficult. See, had it been difficult, they would not have included it in the syllabus, right? If it hadn't been beyond your scope. So this is a Pmp transistor. So this is the emitter terminal. This one is the base terminal. This one over here is the collector terminal. Now I have to forward bias it. So this one is forward biased here. Positive, negative. Here it has to be reverse biased. So positive, negative. If you can check here, both of them are aligned in the same direction. Both of them are aligned in the same direction. This is the emitter current, this is the collector current, and this one is the base current. So overall current through this will be flowing in this manner. So here, because let's not be rigid on this applied voltages, this is VE, VCB. Okay, that's what I said. Okay, that's how people use it in regular usage. They'll not be specific on this. This is a base emitter voltage, this is a collector base voltage. In either cases, the voltage, okay, it is in either cases base is common. Now look here, coming to this, it's as if to this device you are feeding some current through the emitter terminal. Is that right? You're feeding some current through the emitter terminal and you're extracting current from the collector terminal. So this base emitter region Okay, this base emitter region, okay, this base emitter loop, this one is called as input loop. This particular loop is called as input loop, and this one is considered as output loop. Do you agree with this? The base emitter region is called as input loop, and the collector base region is called as output loop or output region. So this is input. So then what must be the emitter current called? Input loop. Correct. So this is output loop. So this is what is called as input current. The collector current must be called as output current. Is that okay? This must be called as output current. Now, in simple terminology, okay, from my experience, if at all I want to judge, if I want to judge how this transistor is simply similar to that of a tank and a tap. Okay, this is analogous to, okay, many of the technical people and scientists, they may scold me for doing so if they come to know, but the logic is something similar to this. You see, emitter is a tank, as in that emitter is a water tank. Emitter is a water tank. Clear? So from this water tank, what you have done is that you have connected a pipe. You have connected a pipe over here. So if I connect a pipe from this tank, and if I connect it to a tap, so and if I'm interested in filling a bucket, if I'm interested in filling a bucket, so this bucket I can consider it as a collector. This one I can consider it as a collector. This is my collector. So whatever is flowing, that is nothing but the current. Okay. Now if you can see simply, if you can simply see this, what feeling is that getting? You see, the logic is simple. If you have water in the tank, that water will reach the collector. That will fill the bucket. If you don't have any water in the tank, that is nothing but any you don't get any water in the bucket, in the collector. Now, does this emitter, whatever present diagram I've drawn, does it give you the feeling of a diode? Is that right? It's like this emitter is a P region, collector is N region. So if it is forward biased, water will come. If it is reverse biased, water will not go. Okay, water will never climb in the reverse direction. Okay, if at all you supply some current, that will reach here. If you don't supply, that it will not reach. Is that right? So it is giving a feeling of diode. Now, in fact, that's the problem with the diode. You see, in a diode, what will happen? If you feed some current, that will reach the collector. If there is some water in the emitter, that will reach the collector. Okay, reverse is not possible. But if there is no current, then no current to the collector. That's the problem with diode. So here, whatever current is flowing through the diode, can you control it? Let's say once you give this connection and leave it, can you control how much amount of water is reaching the collector? How much amount of current is reaching the collector? You cannot do it, right? So that's the issue with diode. So whatever present diagram is there, that is a diode. So if there is some current, it will reach. If you feed some current to the P region, that will reach the N region. But you cannot control the amount of current flowing through it. So that's where there is a requirement, because humans, okay, they are egoists, right? So they want each and everything under their control. So here also, what was happening? The problem is that The problem is that there is an uncontrolled flow. So just to control it, what we do, we put a valve. Is that right? We put a valve, and the name of the valve is nothing but base. Understood? If this base region is not there, so one will be highly doped. I mean, because of the concentration difference, the current will be flowing. But whatever current is flowing, that is an uncontrolled flow. There is no control on. There is no control in our hand. So just to have a control over it, what we do, we introduce base. So what will happen? What will this base do is that this will restrict. Okay, this will restrict the amount of current reaching to the collector. This will restrict the amount of current reaching to the collector. Did you get the logic? That's not exactly same, but this is the logic here. So base current will, the base region will control, okay, will influence the amount of current reaching the collector. So in this case, to exactly understand how this base, is exactly influencing the collector current, okay, or the output current. So what we'll do is that, you see here there are three regions, Pn, Np, and there are two junctions, Pn junction and Np junction, and that too they are forward biased, reverse biased. So we are slightly confused. Okay, we are in a panic mode of. Frankly speaking, even I am frightened looking at the diagram, how to manage two junctions at a time. So for that particular reason, what we'll do is that we'll split. Okay, we'll split this into two separate cases. We'll split this into two separate cases, and in fact we are very well aware of how to solve one particular junction at a time. We know, we are very well thorough with the forward bias mode. A diode which is under forward bias and a diode under reverse bias. So if I split this transistor, what I'll get two diodes. Okay, one is a PN junction diode which is forward bias, the other is a NP junction which is a reverse bias. So let's try to split this into two junctions and try to comment on it. Let's try to split it into two junctions and comment on it. For that, I'm using the space to the left. So here, so first, let me talk about the region. The emitter-based junction. Okay, let me first talk about the emitter-based junction. So let's say this is the emitter, this is the base. For explanation purpose, because we have done it using PN junction diode. That's the reason why I'm using a Pnp transistor over here. But in reality, what we'll be using? We'll be using a Npn transistor. So this one is over here. This is grounded. So whatever is to the right, I'm least interested, because now I'm talking about emitter based junction. I'm interested in emitter base junction. I'm interested only in emitter base junction. So what must happen to emitter base junction? You see, this is a P region, this is a N region. So in a P region, and moreover, how we have connected it, we have forward biased it. Why we have forward biased it? You see, the reason for forward biasing is that this is a P region. It has excess number of holes. So what we want to do, we want to transport these holes to the N region. Okay, even if I say, yeah, I did not forward bias it, what must happen? You see, this is a P region. As in a situation that we did not apply any bias, this is a P region, this is a N region. So N region has excess number of electrons. Clear? N region has excess number of electrons. So in this case, we know that this P region and N region, it will form a junction over here. So the acceptor atoms in the P region, they accept electrons and they become acceptor ions. And the donor atoms on the inside, they donate electrons and they become donor ions. So these are acceptor ions and these are donor ions. Is that okay? Now what is our sole purpose here? we want to somehow, okay, transport. As of now, we do not know why exactly we are doing it, but our main goal is that we want to uh, send this emitter current onto the collector side. We want to send this emitter current onto the collector side. There we want this to reach as a collector current. But as of now, uh, to achieve this, okay, to achieve this, what must happen? The holes over here, they must cross the barrier. They must cross this N region and they must reach onto the collector side. They must reach onto the collector side. To achieve this, tell me, should we forward bias this junction or reverse bias this junction? Here, because the current over here must be because of the majority charge carriers, because we want the majority current to flow. And we know that majority current will flow only when the junction is forward bias, correct? So that's the reason why we always forward bias a emitter base voltage. Here, this emitter base junction is always forward biased. This is always forward biased, so that the charges present over here will be moving to the collector region. This must be moving to the collector region. Now coming to here, in fact, we were considering this everything as our input loop, right? We were calling this as our input loop. Now, if this is our input loop, can you say how will you plot this input voltage versus input current versus input voltage? You see, in the past also for diode, we have plotted, right? Input current as a function of input voltage. Input current as a function of input voltage. So if I try to plot the input characteristics, okay, this one, they're called input characteristics. Input characteristics. Coming to the term input characteristics means we must plot input current as a function of input voltage. Okay, previously, if at all it was a single two-terminal device, okay, it was a regular diode, we would say or any other capacitor, resistor, inductor, all these things, whatever side, we would have applied some voltage, we would have extracted, we would have calculated the current, but it's a thin terminal device, right? So here we say input current as a function of input voltage at fixed output voltage. So we must not forget this fixed output voltage. Understood? First we have to fix the output voltage, then we have to vary the input voltage. Okay, that means first we have to fix the output voltage, then you have to vary the input voltage. Possible try to show. So in this case, if you look at this emitter base junction, what do you see? Here I get to see a there's a complicated diagram. Okay. Actually, I wanted to show this, but here this needs to make some connections like this. See here, this is expected. Here you are expected to make some connections in this manner. So this will do after finishing this. Okay, after finishing the theoretical part, then I'll show this one. Okay. In fact, that's how you do it in lab. So coming to here, all we see is what? All we see is a diode which is under forward bias condition. So in fact, so first you need to apply some voltage so that it will start conducting. After that, the current will rise exponentially. So Vivek is correct. So here you get a curve. Here you get a curve which is rising exponentially. So this is the base emitter voltage. Actually, this should be emitter voltage with respect to base. Simply we call base emitter voltage. So this is the input current. Input current is nothing but the emitter current. So what do you get? This is simple diode, right? Simple diode. So this is nothing but the emitter current will start to flow the moment it reaches when the voltage crosses a certain limit. So if at all it is made out of silicon, then the knee voltage must be how much? 0.7 volts. So actually it was supposed to try start connecting at how much? 0.7 volts. So this is, we simply say for any VCB. We simply write for any VCB, but how will the output voltage influence this input? We'll try to plot another curve. Okay, what will happen if the output voltage is 10 volts, 20 volts, 30 volts? So that we'll try to see. We'll try to draw another graph over here. So let's see how the output loop is functioning exactly. So let's talk about the collector base junction. Collector base junction. Now coming to the collector base junction, let's once again draw this diagram. Okay, we are almost done trying to understand this. The main trick lies here. This is the base region, this is the collector region. This is base, this one is collector. We don't know how to bias it. Okay, now this is the N region, this is the P region. Now what is happening over here? Here there was supposed to be some junction. Okay, and what has happened now? More and more number of holes have entered into this. Okay, these are the incoming holes. These holes are the incoming holes. So holes from here, they have reached here. Now because this is N, so holes have reached into N region, but in reality, actually what is supposed to happen? Basically in N region, there must be only electrons present, excess number of electrons. But now, because you have forward biased the input region, what has happened? All these holes started entering into the N region. We know that in reality, there must be excess number of electrons in the N region. Clear, excess number of electrons in the N region. And there must be excess number of holes in the P region. Now, what is our interest? What do you want? We want all these holes, incoming holes, to enter into the P region. We want all these holes to enter into the P region. Is that right? That means we want the current to be in this manner. Now, here we want holes to enter into P region. That means, are they majority current or minority current? We want here the minority current to flow. We want the minority current to flow. Now, because when will the minority current flow? You see, if at all it is forward biased, the majority current will dominate. Here we want the conduction is due to the minority current. Conduction due to the minority current. So for that particular reason, how we have to bias it? We have to reverse bias this. So positive, negative. So this must be reverse biased. So that's how the collector base region is always reverse biased. Did you get the logic? The collector base junction is always reverse biased. Why? So that the holes, incoming holes, will cross the barrier, because now previously they were majority charge carriers, but now they are nothing but they're simply minority charge carriers. You see, because this is reverse biased, what will happen to the junction width? The junction width also will be huge. You see, compared to the previous diagram, okay, in fact, if you can check here itself in the diagram to show that variation, I have put the junction J1 thin, whereas junction J2 as uh, thick. Why? Because this is forward biased. Under forward bias, the depletion width is less. Under reverse bias, the depletion width is huge. You see, if you put it as unbiased, still the current will flow. But what we want to force all the holes to reach to what? We want all the holes to reach the P region. So that means whatever holes are being accumulated, we want to force them to reach the P region. We want to force them means what we have to do? We have to reverse bias it. You see, we want the control, right? We want to control the charges which are flowing. So we want to control them. So that's how we reverse bias it. So unbiasing is not an efficient way. Ayush. In fact, we have discussed the goal in the starting itself. If you are sending 100 charges, then we want more than 98% of them to reach the collector. So that's why we are making sure that all the charges are reaching the collector. Because if I leave it under no bias condition, there are very high chances. That this current will flow in the towards the base. Understood? If you do not bias anything, so there are very good chances that the majority of the emitter current may flow towards base. You don't want that. We want to force the charges towards collector. That's the reason why we have connected this. Else, if you do not connect this, then what will happen? There are chances to be base current. Now, in this case, if you forward bias it, then what will happen? If you forward bias this, then majority of the current will, the holes will diffuse towards the N region, and all the holes which are diffused towards the N region will be reaching the base. Okay, that's not what we want. We want them to reach the collector. Got the point? So small current to the base, huge current to the collector. Understood the logic? So in fact, this was the reason why we have forward biased the input loop and reverse biased the output loop. So let's try to see how this functions. Let's try to see how this exactly functions. Let's try to plot the output characteristics. Now, by output characteristics, we mean this is not forward bias. So, oh, sorry. Forgive me. This is supposed to be reverse bias. Coming to output characteristics, here we plot output current. Output current means the collector current is output current. as a function of output voltage. Tell me, what's the output voltage here? Collector base voltage is the output voltage. Now, at A fixed input current, that means IA is equal to constant. We first fix the input current, emitter current, then we comment on the output current, output characteristics. So if you try to plot this curve, look here, pay attention please, do not get confused, because from this output graph itself we are going to decide various modes. So actually what must happen, we are reverse biasing the collector base voltage, right, terminals, right? So what must happen, the voltage of the collector base must be represented on the left side. It must be represented on the left side. But people, what they do is that, you see, this is VCB. They purposefully plot the collector base voltage on the right side. That means you can consider that this is the negative terminal, this is the positive terminal. We have flipped the terminals. Did you get the logic? Did you get what I'm saying? Actually, the reverse bias voltage must be on the left side. Forward bias voltage must be on the right side. But here we have purposefully flipped it for our understanding, that because we are right-handers, this is reverse bias, we're plotting it on right, and forward bias, we are plotting it on left. Forward bias means positive volts, and reverse bias means negative voltage. Negative volts on the left side. That's a major alteration which we are doing. Now coming to here, this is the collector current, which is nothing but the output current, which is, let's say, which is expressed in milliampere. Now look here, one logic here. Before coming to this output, let's once go back to the input. Here we said that we have to fix the output voltage. Now my question is, let's say if we change the output voltage, that means if we increase the output voltage, how will this graph exactly vary? Okay, how will the graph vary? So if you have asked, in reality, how this is varying means, let's say this is IE, this is VBE in volts. So I'm hoping that there will be three different graphs from here. Okay, this is, let's say, VCB is equal to 10 volts. Sorry, VCB is equal to let's say, initially I have applied something like this. VCB is equal to this one. VCB is equal to. So what will happen if the output voltage is increased? Now look here. We know that the output voltage must be reverse biased. So if I make it more and more reverse biased, so what is happening? More and more holes which are entering into the N region are being dragged to the P side, that means to the collector region. That means emitter is pumping holes into the N region, and because of the reverse bias, the collector is extracting all these holes. That means is the increase in I mean to say, if I increase the reverse bias voltage, what will happen? More and more holes will be dragged to the collector. That means in the base, the number of holes will reduce. So because the constant number of holes are decreasing, so concentration difference is decreased. So more and more holes will enter from emitter region to the base region. Is that right? So what must happen? That means the increase in the reverse bias voltage will support the flow of emitter current. That means the emitter current will increase. Got the logic here? So if that means the collector current, emitter current will improve. So let's say if this is 10 volts, this is 20 volts, then at 30 volts, what will happen? The the input voltage, okay, the emitter voltage will increase. So if you want to be specific, then 10, 20, 30, the slope increases. Understood? So what we can say, slope increases. As Vivek said correctly, slope increases. The reason is that as emitter note. So here let me put a note saying that as output voltage uh, magnitude increases, it helps the flow of input current. In fact, output voltage magnitude increases. So the better way, okay, the better way, because in the future we may be confused. So what I'll do is that as the output voltage, so I'll say as, instead of output, I'll say as collector base voltage. Collector base voltage instead of output, I make collector base voltage increase. That means as it becomes more and more reverse bias, it helps the flow of input current. It helps the flow of input current. Is it okay? Any confusion? Now let's come back to the output characteristics. Now coming to the output characteristics, so on the right side it is reverse bias, on the left side it is forward bias. So collector current here, this is the collector current. Now tell me, if this collector base voltage is under no bias condition, collector base voltage is under no bias condition. So what must happen? Do you think that the current reaching the collector will be zero? No, there will be some little amount of current flowing through it. Is that right? It is not zero. So we are not drawing the exact graph, but uh, assume a situation. Let's say if you make it purposefully forward bias, that means if you are working against the flow of input current, then if you keep on increasing the reverse bias current, reverse bias voltage, that means if you make it the forward bias, what will happen? You are opposing the flow. So at some particular voltage, it may become zero. But if you reduce that voltage, that means under normal conditions, what can happen? This current through this may be non-zero. Understood? The current through this may be non-zero. Understood? It's definitely non-zero. That means, moreover, at the same time, it is not maximum also. It is non-zero. At the same time, it is not maximum also. But here, I'm trying. I'm considering it as it has almost reached the maximum value. So it will be maximum. Understood? The maximum current is going through it. Understood the logic? You see, here I'm not ignoring the fact that when the input voltage is zero, input current is zero, definitely output current is also zero. Here we're not at all ignoring the fact that when input current is zero, output current is also zero. Look here, in this case. This is IE, input current, is equal to 0 milliampere. The reason for writing capital letters is that I am making sure that it is fixed, right? So I'm using a capital letter. So if the emitter current is 1 milliampere, what must happen? If it is reverse biased, so the collector current must also be 1 milliampere. If the input current is 2 milliamperes, the collector current must also be 2 milliampere. The input current is 3 milliampere, the collector current must also be 3 milliampere. Because we know that majority of the current is reaching to the collector. So here I am taking some freedom in commenting on the values, because nearly 99.8% of the current will be reaching over here. So I'm saying that it is roughly equal, slightly less. Okay, slightly less. You see, in fact, that's the reason here what we have drawn is that slightly less. You see, for 1 it is slightly less, 2 slightly less, 3 slightly less, 4 slightly less. So slight current, okay, of the order of microampere will be leaking through the base, because that is of the order of microampere. So on a scale of milliampere, you will not be exactly able to see it. So whenever you see IE is 0, IE is 0, IE is equal to 1 milliampere, 2 milliampere, 3 milliampere. That means is the input forward biased or reverse biased? In this direction, what is happening to input? In this case, input is forward biased. Input is forward biased. So if you move down along this axis, what is happening? Input is reverse biased. Do you agree? Because the input current is zero, it is not conducting, means reverse bias. If the input is conducting, it is forward bias. So above input is forward bias, below input is reverse bias. Towards the right, the output is reverse biased. So I can say output reverse bias. Here I can say output is forward biased. Is that okay? This is direction where output is forward biased. So here I got 4 quadrants. So if I want to name those quadrants, what I can say here, I can say that input comma output. Input is forward biased. At the same time, output is reverse biased in this region. In this quadrant, input is reverse biased. At the same time, output is also reverse biased. In this region, because it's above, input is forward biased. If you're confused, draw inputs at once. Input above forward biased, below it's reverse biased. Is that okay? Okay, confused, right? Look here. You see, if there is some emitter current, what we know, majority of the current will reach the collector. So if emitter current is 1 milliampere, the collector current is also 1 milliampere. 2 means 2, 3 means 3, 4 means 4. So here, when I have drawn the graph, here I mean that there is some input current, there is some emitter current. So when there is some emitter current, means the input region is forward biased. Clear? So whenever it's 0 or less than that, that means the input is reverse biased. So if you want to say, I can say that if I want to write it as input comma output, if let's say if I'm interested in writing input comma output, so what is happening here? Input above, it's forward biased. Yeah, above it's forward biased. Below, sorry, above it is forward biased input. But what is happening below? Below it is reverse biased. Is that okay? Any confusion from here? Whereas what about the output? On the right, the output is reverse biased. On the left, the output is forward biased. Actually, the graph was supposed to be flipped along vertical, but out of habit, we draw it in this way. The output, we are applying a reverse bias voltage. We are purposefully applying reverse bias voltage. So on the output on the right side is the reverse biased. Whereas on the left, because if you forward bias it, the current will, output current will become zero because you are opposing the flow of input current. So here we got four regions. Now let's start with the region in quadrant 4, reverse bias and reverse bias. Is there any input current? No, input current is zero. What about output current? Output current is also zero. So that for that particular reason, this is what is called cut-off region. This region is what is called cut-off region. Why? Because the device is off. There is no input current. Whenever there is no input current, why will the device function? You have to feed it something so that it will function. So here the input current is zero. So that's the reason why we call it as cut-off region. Now look at forward bias and forward bias region. In this region, in this region, what is happening? From zero output current, it is reaching to the saturation value, right? So that's the reason why we call this a saturation region. Okay, here I do not agree with these people with the naming, because the region in which the current is getting saturated, this was supposed to be called as saturation region. But in fact, they have called this one as saturation region. Okay, the region in which the current is saturated must be saturation region as per proper terminology. But the region in which the current is getting saturated, that one they called it as saturation region. That one they called it as saturation region. So here forward bias and reverse bias. Here input current is fed, output current is extracted. So this you can consider it as active region. This you consider it as active region. And the other one, the remaining quadrant, that will definitely be the reverse active. So in reverse active, what you are doing, you are forward biasing the input. That means you are forcing the current to enter through collector, and you are reverse bias the output. Reverse biasing the input. That means you are extracting current. You are extracting current from the emitter. You see, emitter is designed to emit current and collector is designed to collect it. Whereas what you are forcing by flipping the connections, by reversing both the connections, you are supplying current through the collector and you are extracting from the emitter. Yes, in the reverse bias, it will act like a collector, and collector will behave like an emitter. But will they behave like good collectors and emitters? No, because that's not what they are designed for. So that's the reason why we call it as reverse active region. It's something like a reverse gear in a car. So usually your car, if you want to go to Bombay, so you have 5 gears. Okay, you can travel faster in the forward gears. So you can go on 100, above 100 to reach Bombay. But if at all, you see the car functions in the forward, it can move in the forward direction as well as reverse direction also. But for faster speeds, actually proper usage of car is to use in forward bias, forward gear only. But that means in the active region, let's say there will be some crazy people who want to use it in reverse gear to go to Bombay. You can drive it, I don't have any problem with it, but the thing is that in reverse gear at max you can reach 30 km/h speed, so it will take a lot of time. That means it's not what it was designed for. You can drive to Bombay either in forward gear or reverse gear, but it's up to you which you want to use it. The car is designed to move in forward gear, so we would use it in forward gear. So that's the reason why we use it in active region only. We do not entertain a reverse active region. It's a foolish connection. That means it's not a proper usage of the device. So copy till here. here we have seen how what is happening to the current, how why should we connect the input in forward bias and the output in reverse bias, but what benefit we are getting out of it, that we'll discuss in tomorrow's class. Do you have any class tomorrow, extra class tomorrow? Last Sunday I wanted to take a class, but suddenly Ramrai sir he announced an extra class. Okay then, tomorrow from 9 to 12. Is that okay for you? Yeah, 3 hours with a break. So let's meet tomorrow. Thank you.